好，目前呢看到是没有。那张工呢非常感谢。然后咱们下面一个演讲是 Kvaser 的。在 Kvaser 的演讲之后呢，咱们还会统一，如果大家有问题的话，可以现在再想一想发到 chat 里面，然后可以最后咱们再来讨论一下，并且不一定是要关于这次演讲题目的，任何关于基于 CAN 的通信技术的一些问题都可以提。所以大家现在可以想一想是否有什么问题。OK， 那么我们现在就开始下一个演讲。那么下一个演讲是由 Kvaser 的 Lennartsson 先生来讲的。那么呢，他是瑞典 Kvaser 公司的元老，并且是 CAN 技术的研发的在非常早就已经介入，然后并且呢，他也是 ISO 和 SAE 协会的成员。下面他是讲英语，下面会有实时的中文字幕翻译。并且呢 ，Kvaser 的工程师郑肖俊呢会在最后，如果你有问题的话，他可能会他会给您提供解答。OK， 那么现在我来分享一下屏幕。应该是您是可以听到声音的，如果您听不到的话呢，即使在 chat 里面告诉我，我再调整一下。
Hi, I am Lennartsson. I am Research Manager at Kvaser, and this presentation is about how to secure higher bitrate in CAN and CAN-FT. The goal for this presentation is an understanding of the limiting parameters when increasing the bitrate. The main part that prevents higher bitrate in CAN-FT is the configuration of the bitrate switch bit, but the final blocker is the cable layout and the circuits in the CAN nodes. This figure shows the problem with bitrate switch when different nodes have different sample point location. The arbitration CAN bit in this example have 12, 8, or 10 time quanta in respective CAN node A, B, and C. The figures show that all three nodes are perfectly aligned to the received signal. The CAN-FT controller makes a hard synchronization at the edge between the FDF bit and the res-FT bit. This secures that the res-FT bit always have the sync segment at the edge in the received signal. All three CAN nodes in this example have the same bit length, so there's no clock error to consider. The figures show that even if node A and B have 12 and 8 time quanta, they have the sample point exactly at 75%. Node C have the sample point at 70%, and this is not a problem for classical CAN because the margin to error is normally very large. Different sample point location in CAN-FT is very problematic when using bitrate switch. In this case is node C the sender, and will switch to data bits at the sample point at 70%, but the other two nodes, A and B, will not switch until they reach their sample point at 75%. This will result in a phase offset between the signal and the internal representation of the CAN bits in node A and B. To prevent this phase shift, it's necessary that all CAN nodes installed have the same location of the sample point in the arbitration bits. Also, the data bits have this problem, and all CAN nodes should have identical sample points location also in the data bits. Even if all sample points are common, it's still necessary to handle clock offsets in the bitrate switch bit. In this example, is the data bitrate 4 times the arbitration bitrate. U1 is in perfect sync with the signals from the transmitter after the hard sync. U1's clock is 3% slower than the sender clock. This will cause a 2.5 data time quant phase offset at A in its first data bit. The distance from hard sync to the sample point is almost 7 data bits. With a clock error of 3%, this becomes 25% phase error already in the first data bit. If the bit rate is increased to 10 times, you will get a phase shift of 62%. U2 has the edge late in the sync segment, causing a 4 data time quanta phase offset at C. U2 has a clock that's 3% faster than the sender clock, and this will cause an additional 2.5 data time quanta phase offset at B. This phase offset in U2 will reach the sample point in the first data bit. but the signal edge in error-status indicator bit close to B will trigger sync with logic to relocate the sync segment and by that have a correct sample point in the error-status indicator bit. In the previous slide was the phase offset eliminated by the dominant error-status indicator bit, but this is not true if the sender is error passive. The worst case will occur when the sender is error passive and the first 3 data bits are recessive. This will delay the edge that can be used for resynchronization. This causes an additional offset of 2 data time quanta with the 3% clock offset. So if you have problems with many error frames, then the CAN system becomes more sensitive to phase offsets at the bitrate switch bit. This condition will never occur in a normal test. So, how to reduce or remove this bitrate switch problem? First of all, install CAN nodes with common sample point location in both the arbitration bits and in the data bits. If possible, use oscillator with small variations. Define the CAN bits with as many time quanta as possible. Use the same time quanta length in all installed CAN nodes. The next major problem when increasing the bitrate is the CAN bus layout. The picture to the left is the CAN bus that are used in the following measurements. The figure to the left is a scale view of the cable length used in this test. When you increase the bitrate, it will demand energy at higher frequencies. Higher frequency have a shorter wavelength. When the drop lines and the cable imperfection have dimension close to the wavelength, there will be signal distortion. Any 8-meter CAN bus will work at 1 megabit per second, and any 4-meter CAN bus will work at 2 megabits per second. Imperfection, like drop lines, will add up and increase the problem. This is an S12 measurement on the CAN bus with all drop lines removed. S12 measurements the amount of transmitted energy that will reach the receiver. The top graph shows that the energy level in the signal from 0 to 100 MHz. The 9 drop lines connection points reduce the energy above 45 MHz, which is 4.5 meter wavelength. This bus would work to at least 40 megabit per second. This is the same S12 measurement with the shorter drop lines installed. Here is a huge drop in energy be about 20 MHz, and this will limit the bitrate to 8 megabit per second. This is the same S12 measurement, now with all the drop lines installed. Here is a huge drop in energy already at 2.5 MHz, and this will limit the bitrate to 1 megabit per second. To get high bitrate, it's necessary to use as short drop lines as possible. It is also necessary to reduce the inductors and capacitors between the CAN bus and the CAN driver, because those components will also store and deliver energy. Reduce the slow rates as much as possible. This will remove unnecessary high frequency from causing unnecessary ringing on the CAN signal. If you need long drop lines or have many drop lines, it will limit the possible bitrate. Clusters of drop lines is worse than evenly distributed drop lines. Today there are several CAN drivers designed for CAN-FD, but there is still some more to consider. Try to find a CAN driver with short delays, because that will reduce the propagation segment and provide more phase margin to the sample point in the bitrate switch bit. This will also allow higher bitrate arbitration bitrates, and by that reduce the factor between arbitration and data bitrates. High bitrates demand high slow rate, but use lowest possible slow rate to minimize the ringing and the electromagnetic emission from the CAN bus. EMC filter remove high frequency noise, but also high frequency signals. Make sure you need them. Use EMC filters that match your bitrate. Match the EMC filter to your CAN system, not to the single node. The effect of EMC filter adds up, especially if the nodes are placed in clusters. Here is a list of details that must be considered to get highest possible bitrate. First of all, it's necessary to select an oscillator frequency to get the correct length and number of time quanta in the bit. The length of the CAN bus cable causing delays, which is 5 nanoseconds per meter. The selected CAN driver, because the delay can cause steal 50 meter cable and signal quality. The oscillator quality variation, because 1% oscillator variation is 10,000 ppm. The CAN bit configuration to match the above constraints. The cable quality, so you don't get impedance variation. And also the most important is the CAN bus cable layout, because drop lines cause impedance variation. And to some degree, also the EMC filters can be a problem. The cable delay is given by the speed of light in the twisted pair. The speed of light in the cable is about 5 nanoseconds per meter. At 1 megabit per second is the bit length 1000 nanoseconds. The extent of such CAN bit is 200 meters in the cable. In CAN is all modules equal during arbitration, which limits the cable length to half the bit length, which in this case is 500 nanoseconds and 1 megabit per second, which corresponds to about 100 meters of CAN bus. This graph shows the longest cable as a function of the bit rate. With no node delays, perfect oscillators, 160 time quanta at 1 megabit per second is the CAN bus limited to 99 meters. To understand how delays will limit the bitrate, it is necessary to understand the CAN bit. The bit is sampled in every time quanta sample. In time quanta sample 1 is the level sample recessive, and in time quanta sample number 2 is the level sample dominant, and there must be an edge between the two samples. And the Xiaojun Zheng logger will relocate the SIG segment to the time quanta between TQ1 and time quanta TQ2. Only recessive to dominant edges is used to relocate SIG segment. The phase segment 1 and phase segment 2 must be large enough to secure that the signal edge never reaches the sample point between the two Xiaojun with resynchronizations. Few time quanta in the CAN bit will steal time from the delay budget. The bit edge uncertainty is as large as the time quanta length. This time quanta uncertainty region is named the sync segment. Few time quanta in the CAN bit increase loss of time available for other phase shifts. This figure exemplifies how the edge uncertainty in the SIG segment causes a phase offset in the sample point. Both units U1 and U2 receive the edge at the same time. U8 samples the signal just before the edge and will get the SIG segment after the edge. U2 sample the signal just after the edge and will get the SIG segment before the edge. U1 have the bit sample point at 70% in the signals, and U2 will have the bit sample point at 60% into the signal. This graph shows how the cable length will be limited by the number of time quanta in the CAN bit. This cable length is the theoretical length with perfect oscillators and no delay in the CAN node. So with 100 time quanta is the SIG segment 1% of the bit, and the maximal cable length will be 99 meters. With 8 time quanta is the SIG segment 12% of the bit, and the max cable length will be 87 meters. With 4 time quanta is the SIG segment 25% of the bit, and the max cable length will be 75 meters. To reduce this factor, use as many time quanta as possible in the CAN bit. The main delay source in CAN is the CAN driver between the internal signal and the CAN bus. The delay between CAN driver and the CAN controller is typically small, but could be significant if galvanic isolation is used between the CAN controller and the CAN driver. There is some delay between the CAN controller logic and the microcontroller unit's pins. Here is some typical number. The delay in the CAN driver transmitter is about 120 nanoseconds. The CAN driver has a receive delay also about 120 nanoseconds. Some internal delays between CAN controller and CAN driver could be estimated to about 10 nanoseconds. Galvanic isolation with high performance has typically a 30 nanosecond delay. It all adds up to 280 nanoseconds from sender to receiver without the cable. CAN is limited to a round-trip delay, so we had to multiply by 2, so we add up with 560 nanoseconds of the CAN bit for delays. Select CAN driver and galvanic isolation to match your need and delay budget. This figure shows why delay is a factor during arbitration. Unit U1 start a CAN frame on an idle CAN bus. This starter frame edge is delayed 1.5 time quanta before it reaches U2, and during this time, this unit is allowed to start sending a CAN frame at as late as A. U1 is losing the arbitration at B, and this edge is delayed 3 time quanta and will be compensated by the synchron with adjustment at B. The 3 time quanta at the C will be dominant due to the dominant signals from U2. This graph shows the cable length as a function of bitrate for 3 different delays. A very short delay, 180 nanoseconds, will allow 50 meter cable. A very typical delay, 280 nanoseconds, will allow 31 meters. A very long delay, 380 nanoseconds, will allow only 11 meters at 1 megabit. Also, oscillator tolerance limits the cable length. During arbitration, will signal delay cause phase shift in the first part of the CAN bit, forcing the sample point to the rear. Oscillators with large variation force the sample point to the center of the CAN bit. This reduces the propagation segment, which limits the allowed delay. This page shows the phase shift due to clock offset that is adjusted by the synchron with the mechanism every 10 CAN bits. U1 is at start in perfect sync with the signal, but have a 3% slower clock. After 5 dominant CAN bits is the phase arrow 15% closer to the sample point. After additional 5 recessive CAN bits is the phase arrow 30% closer to the sample point. This recessive to dominant edge will make a synchron with logic adjustment where the sync segment is moved into the edge. U2 has a start edge at the end of the sync segment but has a 3% faster clock. After 5 dominant CAN bits is the phase arrow 15% into the propagation segment. After additional 5 recessive CAN bits is the phase arrow 30% into the propagation segment, close to phase segment 1. There is still 3 time quanta before the edge reaches the sample point, but in worse condition after arbitration, it's possible to start with the edge at the end of the propagation segment. The recessive to dominant edge will make the synchron with adjust the sync segment to the edge. This graph shows the cable length as a function of bitrate for 3 different oscillator variations, 0.5, 1 and 1.5%, with 8 time quanta and a no delay of 280 nanoseconds. With a 0.5% clock, variation will allow 11 meters, but already with 1% clock, you will have minus 8 meter on the cable, which may work, but could cause some error frames off and on. With 1.5 clock variation, it demands minus 28 meter cable. So even if with very short cable, you will probably not have a working CAN bus. Also, configuration of the time quantas in the CAN bit limits the cable length. Mathematically, it's possible to have a typical day 280 nanoseconds, 0.5% oscillator, an 8 time quanta at 1 megabit, and a CAN bus with 11 meters with a sample point at 85%. But with 8 time quanta, the closest sample point is 75%. This will increase the sample point protection, but this will limit the propagation segment to 3 time quanta, which equals 375 nanoseconds. But with a delay of 560 nanoseconds, no delay, demands a combo length to be shorter than minus 90 meter. A negative length in the cable is not physically possible. So the only solution here to make it work is to have more time quanta in the CAN bit. So now this question, how do you handle long delays or oscillators with large variations? In this case, lower the bit rate, because if you move from 1 megabit to 500 kilobits, the 3 time quanta will be 750 nanoseconds. This has no cost, but it will reduce the bandwidth with 50%. You can also use more time quanta in the CAN bit. This demands a faster clock, would probably increase the cost. You can use better oscillator, better quality, increased cost. You can use CAN drivers with less delay, CAN-FD CAN drivers, which probably cost more. Use galvanic insulation with less delay, cost more. Remove the galvanic insulation, that will remove the cost, but it will be a less robust product. And the other option which available for us is switch to CAN-FD and use the bitrate waste and increase the bitrate when in the data path. I have written a paper describing this presentation, and also in CiA there is at least 3 papers talking about this problem. It's CiA 601.1, 2, and 3, which you can download from the CiA homepage. That was all in this presentation.
好的，那么Kvaser 的分享就结束了。如果有针对 Kvaser 的分享的问题呢，咱们现在可以提一下。Kent 呢也在线上，他也会专门给咱们回答。好，另外呢，如果大家还有一些其他问题的话呢，现在也可以提。所以咱们就提前进入这个自由讨论的时间。大伙现在可以思考一下是否有什么问题。那我现在呢就是回答一下刚才关于这个我的演讲 KSL 里面有致远的黄美思经理提了一个问题，就是 KSL 隐性也有驱动，那它怎么进行仲裁呢？就是一个节点它发显性，一个发隐性，那怎么驱动呢？这个的话呢它是针对于一个这个就是 CiC 收发器的一个问题。这个 CiC 功能呢，就是 Signal Improvement， 它是在这个 CAN-FD 的收发器这个CAN-SiC transceiver， 并且呢，在这个新型的 CAN-SiC XL transceiver 里头也有使用。所以说这2个新型的收发器呢，都会遇到这个问题。那么它是怎么解决的呢？我可以给您看一下，这是我以前的一个演讲，就是说，就是说为了达到这个正常的仲裁，那么这个信号改进的这个阶段，它就必须要在所有的这个信号传递一遍，通过所有拓扑传递一遍的这个之后，它的之前就必须要结束。那么所以说，它对于隐性位的这个驱动就不会影响下一个位。那这样的话呢，就不会对这个仲裁造成任何的问题。那么呢，这个的话呢，我们是规定在这个601-4的文件当中，就是专门规定的这个信号改进功能，它里面规定了一些时间参数，就是说它的参数的意义就是说，所有的这个时间的这个传输时间，你可以看到，所有可能会产生延时的地方，它所有总的和，那么它这些延时都必须要在我传输下一位关于仲裁，就是仲裁位之前都要结束。所以说那么的话，这样的话呢，就不会对这个仲裁产生误读。那它这个就是它的一个这个信号改进功能的一个主要原理。具体的它规定的时间参数呢，您可以到601-4的文件，它后面有一个附件，可以去查看。好，如果目前没有看到有其他问题，那如果没有其他，我又看到一个问题，可以在CAN-FD的收发器上发CAN-XL 的协议，那么请问总线上的电压怎么区分？因为 CAN-FD 的电压是 2.5， 那么 CAN-XL 的数据端的电压是 Level 1和 Level 2。对，您这个确实是一个点。那么，事实上，这个 Level 1和 Level 2的这个，就是我刚才也讲到了，这个它是一个 fast mode， 这个 fast mode 也是可开可关的，所以说您不是必要使用 fast mode。如果您使用了 CAN-FD 的收发器，那您当然就不会使用 fast mode 了，所以说就不存在这个 Level 1和 Level 2的问题，就是应该是 Level 1和 Level 0，我记得不是 Level 2。那样的话，您就是等于说使用 那您所得到的这个 benefit 就是说一个很长的针，通过 KSL，就不会使用这个快速传输的这个优势了。所以说还是要考虑，就是说，您对于您的需求，您需要达到多少的一个数据的传输速率，然后呢来选择。另一个问题是，重同步是不是在每个隐性到显性跳变都进行呢？这个应该是的，这个是的。在仲裁阶段的话是都进行的，但是在数据传输的阶段应该是不是都进行的？我的理解是，如果我说的不对的话，咱们大伙也可以纠正我啊。
在数据端应该也是的，就是
是吗？
对，就是你其实每次就是发送隐性到显性嘛，你就所有的接收节点都会进行一次重同步。那么关键你说，
但是在看 SL 的这个数据端的话，应该就不会进行。
对，因为 KXL 的话是有所不同啊，他提的是 KXL 对吧？
对，所以要分着讲一下。KNF 就是只有 KNXL 的数据段是不会进行的，那么在其他的阶段都是要进行的。
对，
好的，谢谢您。好，那么大伙有问题的话可以再提，我再等2分钟。那如果没有问题的话，2分钟后咱们就结束。那么我在此呢感谢一下这次呢协会主席蔡图旺先生，然后并且呢红科的万工，然后恩智浦的张工，然后还有Kvaser的 Kent 对咱们这次活动的大力支持。然后 CiA 呢会一如既往的给您提供关于这个协议方面的解读，还有这方面的问题的支持和解答。然后呢也非常期待在以后如果情况好转的话呢，我们能够在中国面对面的进行交流。然后呢这个希望咱们 CiA 的会员在国内也都多多进行交流。然后因为大家都是有最新一手的关于 CAN 这方面的技术的更新，所以说大家多多交流呢，也可以促进行业的发展。好，那侯哥已经走了，他下面还有一个会。好，那我看目前应该也是没有什么其他问题了。您后续有问题的话，可以随时给我们发邮件啊，或者是关注我们微信公众号，或者是直接给我发微信也可以。那么就非常感谢大家的参与，希望您关注我们后续活动。那么这次就这样结束了，那就和大家再会，以后咱们再见。
好，谢谢，拜拜。
谢谢。
谢谢，拜拜。
拜拜。